Most students will think that electromotive force is a type of force. They will not actually know or understand that electromotive force is not actually a force. Yes, electromotive force. Alright, hello guys, I'm Abgenius. Welcome to my YouTube channel once again. And today we're going to be looking at practice problems on dimension of physical quantities. And we are going to be looking at on how to solve some problems related to dimension. Just in case you are not very deep in the understanding or the knowledge of dimension, I would like you to go check out my video where I have explained the meaning of physical quantities, their types, how to derive their units, and as well I gave a robust introduction to dimension of physical quantities. Are we together? And that reminds me, if you're new to this channel and you're not subscribed to the channel, I would like you to please kindly like the video and subscribe, so that anytime we post any video that will be helpful to your academics or to your knowledge of science entirely, you'll be notified. All right, so we're going to be diving straight into what we're having to do. So we're looking at a physical quantity that has the same dimension of impulse is A, energy, B, momentum, C, surface area, D, pressure. All right, remember in that first video I had done, I had defined dimension of quantities as the powers to which the fundamental quantities that make up that quantity is raised to give that particular quantity. So we're looking at impulse now. We are looking at what are the powers of the fundamental quantities which are contained in impulse that will give us impulse as a quantity. Are we together now? And that is in practice. And so we are going to be looking at how to solve this problem. Now, most persons might like to take different approach, but if you look at this problem, I think this question is very simple and you can solve it in just a second. What I mean is that some persons might want to start solving for the dimension of energy, and then solve for the dimension of momentum, and then solve for the dimension of surface area, and then the dimension of pressure, and then they'll not start comparing when they have also solved for the dimension of impulse. That will be time consuming. But I'll just give you a simple trick to get what you need or the answer to this question. So solution quickly. What are we looking at here? We're looking at what? Impulse. Now, impulse, from Newton's second law of motion, we derive that impulse is equal to force times time. That is impulse. However, before we derive this, we got that impulse also is, remember, its impulse also is equal to change in momentum. Change in what? Change in what? Momentum. So if we take impulse as change in momentum, change in anything still gives us that same thing. So with respect to dimension, impulse will have the same dimension as momentum. And so that makes option B to be the correct answer. Are we together now? Because if impulse is equal to change in momentum, then change in momentum will still give you momentum. Because you just say final momentum minus initial momentum, and that will give you change in momentum. So it will still give you momentum, and so it will give you impulse now. So impulse will have the same dimension as what? Momentum. And just in case you would like me to post a video on Newton's laws of motion and to solve problems on linear momentum, you can please notify me by dropping it in the comment section, and I will see to it to make such videos. Are we together now? All right. However, if you want me to go ahead to prove that the correct option to this question is momentum, then I'll have to do that. So I'm going to cancel off this or erase this change in momentum. Now I'm going to derive the dimension of what? Impulse, and then keep it and start comparing it to these other four options. So I'm going to first of all get the dimension of force. The dimension of T is capital letter T because it's time. Remember, we had said that the fundamental quantities are, the basic ones are length, mass, and time. In dimension, we denote length as capital letter L, mass as capital letter M, and T as capital letter what? T. I would like to add to the list that electric current we denote it as capital letter what? I. All right. So what it means, wherever you see any of these, you're going to substitute the value for it. Now we know that force is equal to mass times what? Acceleration. And the dimension of mass is what? Capital letter M times, I have to go get the dimension of acceleration. Acceleration is equal to change in velocity over time. However, for the purpose of dimension, I will take it to the velocity over time, because change velocity over time or change in velocity still means velocity. So I'm going to write as what? Velocity all over what? Time. It simply means that I will still have to what? Go derive the dimension of what? Velocity. You know that velocity is equal to displacement all over what? Time. Now remember, I had told you in that previous video also that distance, displacement, height, breadth, width, they all represent what? They all represent length. They are in the dimension of length. So if I take that, I'll have that displacement is what? L over T. And by if I simplify it, to give me L times 1 over what? T. Remember, I'm interested in the powers of the fundamental quantities. So to get that, this L 1 over T can be written as 6 to the power minus 1. I explained this in the previous video as well. So what I'm going to do, this is the dimension of velocity. I'm going to substitute it here. Instead of velocity, I'll put L T to the power minus 1 all over time is what? T. Now, how did we get this L to the power minus 1? We got it from L over T. So I write that L over what? T, then divided by T. And that will boil down to give me what? L over T. Then this division becomes what? Multiplication. Reciprocal of time, 1 over what? T. L times 1 gives you L. T times 2 gives you what? T squared. To bring this up, I'll write L to the power minus 2. That's the dimension of acceleration. So I'll just bring that value or this to this side. That becomes L to the power of what? Minus 2. Join them together. Dimension of force becomes M L to the power of what? Minus 2. So I'll substitute for force what the dimension is. It becomes M L to the power of minus 2 times T, which is time, is capital letter T. And that will give me, to simplify this, I'll write M L. Remember that if anything has negative power, then it's probably going to be in the words denominator, but with the positive power now. Then times what? T. Alright, so to simplify this further, I'm going to have that this becomes what? You know, T square means T times T. So let me write it as T times T. So 1 T will cancel out 1 T. That will give me M L series to the power of what? Minus 1. Or let me write it as first M L over T, because M L, the power of T here is 1. Bringing it up becomes to the power of 1 minus 1. This becomes the dimension of what? Impulse. So trying to compare other ones. Are we together now? Alright, looking at energy. Energy is the same thing as work. And where work is equal to force times displacement D. And if you are comparing that impulse is equal to force times time, obviously, because of this value, this energy or work cannot be in the dimension of impulse. And so energy is a wrong option. And then let's look at surface area. Surface what? Area is actually equal to force over length. And we are looking at force times distance. This is force divided by length. It cannot happen that surface area will be in the dimension of impulse. And so it's also a wrong option here. And then looking at pressure, pressure is equal to force all over area. Force over area, force times time, it is also the wrong option. Now let's go to momentum. If you go to momentum, you know that momentum is actually equal to mass times velocity. It's the product of mass and velocity of an object. Are we together now? And if we take that mass is capital letter M times V, remember I've just derived the dimension of velocity to what? L series to the power of minus 1. Join them together, have it as M L series to the power of minus 1 to be the dimension of momentum. And you see that corresponds with this. Therefore, the correct option still remains what? Momentum. Alright, second question. The dimensions of electromotive force are these options. We're going to find the option that gives the correct answer to this question. Now, most students are going to be confused there because of this quantity force. In fact, electromotive force. Most students will think that electromotive force is a type of force. They will not actually know or understand that electromotive force is not actually a force. Yes, electromotive force is a potential, is work done. So if I'm to define electromotive force, which we also write as EMF, that is the way we abbreviate electromotive force. It's not a type of force. So if I'm to define EMF, the electromotive force of a cell is the work done by the cell in moving a charge of one coulomb round the circuit. That is electromotive force or EMF, and it is given by the symbol, or denoted by the symbol E, is equal to work all over charge. Are we together now? Work over what? Charge. This is the formula for electromotive force. And so if we can try to express the fundamental quantities which these quantities that make up EMF contains, we can successfully get the dimension of EMF. Are we together? Remember, I had said that length is the same thing as what? Is denoted by capital letter L, mass, capital letter M, time, capital letter T, and then current, electric current, precisely, capital letter what? I. And so, what is work? You know that work is what? Force times what? Displacement or distance. And what is charge? What is charge? Q. Charge Q is quantity of charge. We have learnt in electricity that current I is actually equal to the rate of flow of charge. Is the charge flowing through a conductor per unit time. Are we together now? And so from here I can get that my Q is equal to what? IT. So this is the formula for charge, and so I can put it here, I times T. So my job is to get the dimensions of each of these, and then I substitute and solve. So look at this now. I'm bringing in force. Remember, we have just derived the dimension of force through what? MLT raised to the power of minus 2, and this displacement, they are all lengths. So put it as L all over. Current is what? I. Then times time is what? T. So what I will do is to try to solve all of this problem and to get my final answer. Now I'm going to take it this way. This will become M L. Remember that n to the power minus 2 probably used to be in the denominator, but with the power positive, times what? L. Are we together now? That I'm working with the what? With the numerator, divided by, let me put it as IT. Okay, IT. And so I'm not going to know this. I times T is IT. So I'm not going to solve that. Let me bring it up here. So I'm not going to solve that. M L over T squared times L. Then the division sign I'll put times. Then 1 over IT. I'm going to see if I can cancel out something to get my value. All right. So now let's get the numerators. M times L times L times 1. Well, L times L is L squared. So M times L will give me ML squared times 1. That becomes what? ML squared, right? Over, denominator that take this to over 1. T squared times I times T. Remember that this is raised to the power of 1. So from indices, T to the power of 3 times T to the power of 1. Since the bases are the same, I take one of the base and add the power. Okay, I'm dealing with 2 rather. Okay, so this is 2. That will give me 2 plus 1. That will give me T to the power of 3. T cubed. So T squared times T will give me T cubed. Then times I will give me I. So T cubed I. And so if I want to get the final thing, I'll write it. Let me write it this way. M L squared. If you are denominator, to bring it up, it become negative. So it become minus 3. Then I is the power is 1. So it become minus 1. And so it means that the dimension of EMF E is now M L squared T to the power of minus 3 I to the power of minus 1. So let's go ahead to check which option contains this. All right, and M L square to the power of minus 3 I to the power of 1. Okay, I did not put that this is minus 1. All right, so minus 1, and obviously option A is the answer. Very simple, right? The next question. All right, the value of x, y, and z respectively in the expression this for the universal gravitational constant G are, we have options to solve it and to check. Are we together now? All right, so let's go into it quickly. Now, if you are looking at universal gravitational constant G, this is coming from the topic Newton's law of universal gravitation, and it states that every particle in the universe attracts every other particle. Precisely, every massive particle that has mass attracts every other particle in the universe with a force which is proportional to the product of their masses and inversely proportional to the square of the distance between them. Now, this law was propounded by Sir Isaac Newton, one of our boss in physics. Are we together? And it's actually called also the inverse square law. And so, with what I've said, the law said that the force of attraction between two particles that has mass is proportional to the product of their masses. So let me say the masses are m1 and then m2, and also inversely, I'll put over for inversely proportional to the square of the distance r between them. And so, removing the positive sign and putting a constant, I'll put g, then m1 m2 over what? R square. Are we together now? Take note that the value of g is equal to 6.67 times 10 to the power of what? Minus 11. So we are looking at what are the values of g that will give us the dimension for it. And so for us to do that, from here we are going to make g the sort of formula. Doing that, multiply both sides by what? R squared. So we have that f r squared is equal to what? G m1 m2. Next thing is to divide both sides by what? m1 m2. I have it this way, m1 m2. This will cancel out, so g becomes equal to fr squared over m1 m2. This becomes the formula of what? Of gravitational constant what? G. And so we can go ahead to derive the dimension for G. Okay, now doing that, we have to get the dimension of force. We have derived that in the first question. That will give us what? M L C to the power of minus 2. Then remember that arrow is actually what? Distance. It's actually distance. Okay, remember distance is in the direction of what? Length. So this will become times L raised to the power of what? 2 all over. We are having mass 1 times mass 2. That will give us mass times mass. All right, quickly I just have to cancel this. Are we following now? Because it appears on the numerator and the denominator. I will have everything to give me as what? L to the power of minus 2 times L to the power of 2, right? All over what? M. Now, L times L squared. The power here is 1, so the bases are the same. I'll take one of it, right? And then I'll add. It becomes what? 3. 1 plus 2 is 3. So I now have 2 to the power of minus 2 over what? M. I don't know who said so, but dimension is in the order MLT. However, the power of M here is what? 1. And so remember, for us to bring M up, we have to do what? We have to make the power to become negative. And so I'm going to write that what? This is now M, the power is 1, becomes what? Minus 1. And then I'll bring L is to the power of what? 3. Then T is to the power of what? Minus 2. This becomes the dimension of what? Of G, the gravitational what? Constant. And so what I'm going to do, I'm going to compare this I've gotten what I was given. That's M, X, L, Y, then T is to the power of what? Z. Now comparing, the power on M is minus 1, or minus 1. The power on M here is what? Is X. So X, let me bring it up. All right, so we have that this becomes what? X is equal to minus 1, Y is equal to what? 3, and then z is equal to minus 2. And so which value is in that order? Minus 1, 3, minus 2. 2 minus 3 minus 2, minus 1, 3 minus 2. And so option B, the correct answer. Alright, the next question. Alright, this question is a bit lengthy and we're going to be doing a lot of things here. So please pay attention, and I would like you to, if you can, have your pen and your book beside you to join me to solve. Alright, a small mass is suspended from a long thread so as to form a simple pendulum. The period t of the oscillation depends on the mass m, the length l of the thread, and the acceleration g of free fall at the place concerned. We are given this equation and we are told that x, y, and z are unknowns and k is equal to 2 pi. We are asked to find the values of x, y, and z, and hence derive an expression relating t, m, l, and g. Well, I usually used to like this kind of questions because they are tasking. Yes, I love tasking things. So we're going to be solving this problem now. The first thing we're going to do is to try to find the value of x, y, and z. And it's super simple. Why? Because if we can get the dimension, like if we can replace this in dimension and then compare the values of what we have with x and y, just like we did for the initial question I just solved now, we can just get the answer. So we're going to write the equation given to us. T is equal to k, m is the power of x, l is the power of what? Y, and g is the power of what? Z. Are we together now? And you have to be very sure you know what each of the letters stands for. We are told that the mass, the m is what? Mass, l is what? Length, and g is acceleration. Now what we do now is try to get the dimensions of each of them. Are we together now? Remember that period t, remember they told you that period is t, and period is nothing less than the time taken to complete one oscillation. So remember I just said time, so period is t time. So the dimension of t is what? Of period is t, capital and what? T. Are we together now? Equal to k is a constant. We are told that k is a constant, and so every constant does not have a dimension. So I will not bring in k because it is dimensionless. Now I'm going to write now that what? Bringing that dimension of m, which is mass, and calculate that m, that is the power of x, l, which is calculate that l is the power of what? Y, g is acceleration, and we have derived that the what? That the dimension of acceleration is l t is the power of minus 2. So I will replace g, which is acceleration, to the what? L t is the power of what? Minus 2. That's, this is just g. Then I put z, which is raised to. So I'll simplify. T is equal to m raised to the power of x, l is the power of y. Then I'm going to distribute this z to everything in the bracket according to power law, because in indices now the power of l here is 1. So 1 times z is what? Lz, let's suppose z rather. Then this minus 2 times z now give us what? Minus 2 what? Z. And so I just have to apply indices here to get a common value for our what? For our length. So I have m is the power of x. The bases are the same. I have to add the power. That's y plus what? Z. Then t is the power of what? Minus 2z. Now at this point in time, what I have to do is to ensure that all the fundamental quantities that are on one side of the equation must appear on the same side of the equation. Remember in that first video I did, I gave that the dimension of area was l is the power of 2. However, I also said that if we want to include other fundamental quantities, that we can write it as m is the power of 0, then l is the power of 2, and then t is the power of 0, because anything to the power of 0 is 1. So this will give us 1 times l is the power of 2 times 1, and then the figures was l is the power of 2. So if I want to include the fundamental quantities that are not in that equation or that formula, I will just put them but raise them to the power of 0, because they will give me 1. So I want to make sure that everything that is here is something that is here. Doing that, I'll have m raised to the power of 0 because t 1, then l raised to the power of 0 is t 1, then t, of course, is raised to the power of 1. Let me just put the power. So you have this as m raised to the power of s, l raised to the power of y plus z, t raised to the power of minus 2 what? Z. And so now we are looking for the values of x, y, and z. We're taking the first question. And so what we're going to do now is by comparison. By what? Comparison. So comparing, if you check here, you have that. If you check from here to here, see that x is on m and z is on s. So you can see that x is equal to what? 0. Are we together now? And then we can have that what? Y plus z is equal to what? 0 as well. Are we there? Then minus 2z to 1. So you have minus 2z is equal to 1. And so if you want to solve this, we are getting that x already is equal to 0. you are getting the value. So because this is y plus z is equal to 0, I can use the third equation to solve and get z and substitute it into the second equation. So doing that, I will not, let me solve it here. I'll have that what minus 2z is equal to 1. Divide both side by minus 2, have it as what minus 1 over 2, and this will cancel that. So z is equal to minus 1 over 2. I'll bring it here. So okay, let me keep it there first. Now I'll not solve for y. You know, y is equal to y plus z, that's minus 1 over 2 is equal to 0. Are we together? Bringing it up here, let me finish it up here. We have that y plus times minus is minus, so we have y minus 1 over 2 is equal to 0. Let's take minus 1 over 2 over to the other side. It becomes y is equal to 1 over 1 2. So we have that now that y is equal to 1 over 1 2 and z is equal to what? Minus 1 over 2. So for the first question, which is I, we are getting that what? For the first question, let me clean up here. We are getting that what? That's for I. We are getting that x is equal to 0, then y is equal to 1 over 2, and then z is equal to minus 1 over 2. These are the values of what? Of z. Next is to do what? Is to derive an expression relating T, M, L, and G. So what we do, we go back to the equation given to us, because we have to include the constant here, because in deriving the expression we don't need dimension, and since k is a constant, we're not going to throw it away because we don't have dimension, so it will come back. We proceed it during dimension because it is dimensional, because now it's going to come back. So I write T is equal to k m to the power of x, l to the power of y, and then g to the power of 1 z. So substitute the value of each of these and we get the answer. So T is equal to k. Remember that k was given to be 2 pi, right? That's what 2 pi, right? M, you know that this s is equal to 0, then L is to the power of 1 over 2, then G is to the power of minus 1 over 2. Of course, these are all multiplying themselves. Are we together now? And so to finish up from here, I'll quickly say that T is equal to 2 pi, n to the power of 0 is 1, and so 1 times this times this, these are the same thing. Now L is the power of half, n to the power of half is actually square roots. This is square root of L. Are we together now? Okay, times from indices, this is negative index, so I have to write this as 1 over G raised to the power of half. That's if you remove the negative sign, put up 1 over this. So T now becomes 2 pi square root of L times 1 over just the power of half is same than square root of G, and so this will bother to give us what? T is equal to 2 pi square root of L times 1 square root of L, and then I will have my denominator to be what? Square root of G. This becomes the expression that relates T, M, L, and G. Just in case you also want me to derive this in simple harmonic motion, I will also do that. Kindly put that in the comment section, and please, if you have not subscribed, please, I would like you to do so, so that whenever we post a video you can be notified. Also make sure you like and then comment. Make sure you also send this video to your friends whom you think will find it very useful. If you are writing JAMB, WAEC or UTME, WAEC and NECO, the SSCE, this video I've just done is also useful to you, and more of our uploads will also be useful to you. For now, bye. I remain Mav Genius.